Hello, and welcome to the session where today we are talking about cost behavior, and our focus is on linear cost functions, methods of estimating mixed costs, and nonlinear costs. So let's jump right in. When we talk about linear costs, what are we talking about? Well, the term linear simply means straight. Therefore, linear costs are those costs that will maintain a straight line. And we can see this in two different ways, where total fixed costs will remain constant and unchanged, or variable costs per unit will remain unchanged. Let's refresh our memories with total costs. Total costs will equal the sum of total fixed costs and total variable costs, as we see in the equation there on your screen. Total costs equals total fixed costs plus total variable costs. Now we can put this into a linear cost function. A linear cost function is simply a mathematical expression of how total costs will change when there is a change in activity level. For example, my total cost should go up the more I produce in total, and my total cost should go down the less I produce. And this cost function is just simply a mathematical expression to let us estimate costs, or what total costs will be at a given level of activity. So let's break down this formula here. Y. Y in the equation is going to be total cost. A will simply represent fixed costs. B will represent variable cost per unit, and then X will be the number of units. So it kind of makes sense. My total costs, Y, equals A, my fixed costs, plus B times X, my total variable costs. So let's take a look and review the types of costs, variable and fixed costs. Remember, we talked about before variable costs. These costs remain the same on a per unit basis, but the total costs incurred will vary in direct proportion to the level of activity involved. So I can state this linear cost function in this graph would be Y equals 20x. Y, my total costs, if this is a pure variable cost, then my Y, my total cost, is going to be 20 times X, and let's assume that the cost of labor is $20 per hour. So if the cost is $20 per hour, if an employee worked 30 hours, a linear cost function would look like this. Y, my total cost, would be $20 per hour times the number of hours worked. And if the employee worked 30 hours, my total cost would be $600 for that cost of labor. So therefore, an employee who worked 30 hours would cost the company $600 in labor. Now let's take a look at fixed costs and just remind ourselves of these. Now these costs will change inversely on a per unit basis with the level of production, but the total cost incurred will remain the same given that relevant range. So the linear cost function in this graph would be stated as Y equals A. Remember, A represents fixed costs. So my total costs, if my cost is fixed only and there's no variable component of that, then my total cost is going to be equal to my fixed cost. So if a company is using straight line depreciation, the amount recorded will remain the same regardless of how much or how little an asset is used. So for a fixed cost, the cost function would look like this. Y equals A, so then Y equals 10,000. So that is an example of my cost function for a fixed cost. So my cost function would be, for variable cost, would be Y equals 20x or BX. And then for a fixed cost, my cost function will be Y equals A, in which my total cost will be equal to my fixed cost. And that's, again, because there's no variable component in there, my fixed cost will also equal my total cost. Now let's take a look at the total cost, and the linear cost function would be expressed as we just talked about this a couple screens ago, Y equals A plus BX. So let's assume that a company has fixed costs of $3,000 and variable costs are $5 per unit. If we wanted to know the total cost of producing 2,000 units, we would calculate it as such. We take our formula, we take our linear cost function, which is Y equals A plus BX, and then we just plug in the numbers into the formula. If my fixed costs are $3,000, I'm going to plug that into A, and replace A with $3,000. My variable costs are $5 per unit, and I'm going to make 2,000 units. So I'm going to plug $5 per unit into B, and I'm going to substitute 2,000 for X. So when I take the next step in computing that formula, Y equals $3,000 of fixed cost plus $10,000 of total variable cost, $5 per unit times 2,000 units. So my total cost of producing, 2,000 units is going to be $13,000. So that's where we get a chance to estimate these costs based on the linear cost function. And that linear cost function is going to be helpful in a number of situations in order to solve problems, in order to figure out how much is it going to cost me. So that is a formula that would be very helpful to you. In fact, if you've taken any type of algebra class, you know that is a similar expression to the slope-intercept, or the formula for measuring a slope. So just a little math nerd in me. Okay, so when we're looking to identify cost drivers, first thing we want to do is understand that we're looking to estimate past costs based on the levels of activity in their relationship to past cost data. Why are we using cost estimation? So we can use cost prediction, so we can make predictions about future costs. So when estimating a cost function, we have to determine whether the cause-effect relationship, whether there is a cause-effect relationship with the level of activity and the cost associated with it. Why? Because there's going to be times where we're assuming a cause-effect relationship, and on the surface, on paper, it may look like there's a relationship, but there's not. There may be correlation, but not causation. So now there are three ways to identify a cause and effect relationship and how it might be realized. One, a direct physical relationship between the cost and the levels of activity. Two, a contractual agreement. And three, knowledge of the operations. We're talking about a direct physical relationship with costs and levels of activity. We can identify that the cost function for a direct physical relationship between cost level and activity, cost and level of activity, well, the more direct materials we put in, then the higher our total costs are going to be. So there is obviously a direct physical relationship there. What about a contractual agreement? Well, we might have a contractual agreement where if we have a contract stating this many units will cost this much, this many units will cost that much, then we have a contractual arrangement. And finally, knowledge of operations, where someone might be very knowledgeable about our operations. They know our operations inside and out. And so one of our managers may be able to estimate a cost function based on their knowledge of our operations. For management purposes, we want to try to establish a cause-effect relationship as much as we can with a direct physical relationship between the cost and levels of activity. But just because there's a correlation and the cost associated with it does not mean the activity is a cost driver. So just because total costs increase and the level of and the units of activity and let's say labor hours are increased, and then my total overhead increases, well, they may be going in the same direction, but labor hours may not be the best cost driver for that overhead cost. So just because there's a correlation between the activity and the costs associated with it, or the assumed cost driver, does not mean that activity really is a cost driver. So we could assume that there's cost drivers or activities that we think are cost drivers, and they're really not. They happen to move in the same direction, but they may not be the actual cost driver in and of itself. And we'll talk just a little bit about that in just a few moments here. So now there's going to be four methods of estimating costs. One is the industrial engineering method. And we talk about, in the industrial engineering method, analyzing the relationship between inputs of a cost object and the outputs of completed units. This is mainly done with time motion studies. I know you've heard about that in other classes here, so I won't go over that. But these time motion studies are utilized to aid understanding and the relationship between the two. Then we have the conference method. The conference method is an agreement on estimated costs and their drivers by personnel from different departments within a company. Basically, we're taking personnel from different parts of the company, we're getting together, we're all looking at this data, and we're just saying, hey, you know what? Let's come to a consensus there. Then we have the account analysis method, where we're going to classify each cost as variable, mixed, or fixed. And then we can use that to, estimate our costs. And then we're going to do quantitative analysis method. And this is a formal mathematical method to create cost functions based on past data. And this is probably the best way to do it in most situations. We have two ways to do that. The high-low method, which is not as accurate, but it is quick and easy to understand and to calculate. And then we have regression analysis, which is a statistical method, which we'll take a look at here in just a little bit. Now, both quantitative analysis methods, whether it's the high-low method, the regression analysis method, will depend on classifying or identifying data as independent variables or dependent variables. So let's define dependent variable for our situation. The dependent variable is going to be the cost we want to predict. So when we go back to our cost function, when we do y is that total cost we want to predict. That is going to be our dependent variable. The independent variable is going to be the cost driver or the level of activity. And that would represent X in our cost estimation formula, because that's going to identify, because we expect that the higher the level of activity, the higher my total costs are going to be. So, and let's just take a look here. Okay. So let's do a look at the first quantitative analysis, high-low method. Now, the high-low method of estimating costs bases information on the highest and lowest amounts of the cost driver used and the total cost associated with those amounts. And there are three easy steps to using the high and low method. We want to determine the variable cost per unit, which is the slope coefficient, determine the fixed cost per unit, and then create the cost function equation to estimate costs at different levels of activity. And in fact, let me go back here just a few screens here. This right here, the B, that's my variable cost per unit here. We would refer to that as the slope coefficient. So in the chart here, my slope coefficient is how much my costs are going up over the range of activity. And so we would associate that with variable costs. So in the illustration here, my slope coefficient would be $20 because that's my $20 per hour unit. So I just want to make sure I touch base with you on that, and that B is going to be represented as my slope coefficient. So now let's go back here. So I want to determine the slope coefficient, then I want to determine the fixed cost per unit, and then I want to create the cost function equation to estimate costs at different levels of activity. Now, I stated earlier, while the high-low method is a quick way to estimate total costs at any level of activity, it's not highly accurate. Why? Because we're only focused on the highest level of activity in a given data set and the lowest level of activity in the data set, and then their corresponding total overhead costs. So let's take a look at an example, and let's look at Acme Corporation. They provided the following data. And they give us a cost table there and the associated cost driver, which they believe is going to be labor hours. So we have a cost there. The first period is $3,200 associated with 80 hours of labor. The next period is $3,900 worth of total overhead costs. And then we have $110 hours of labor. $4,500 of total costs associated with 120 hours worth of labor. And then finally, $3,600 worth of overhead costs associated with 90 hours of labor. So let's put the three steps into motion here. The first step, we want to determine the slope coefficient or the variable cost. So how am I going to do that? Well, I'm going to take the highest amount of overhead and the lowest amount of overhead. So I'm picking out my highest and lowest data points. So what are my highest and lowest data points? Well, my highest and lowest data points here, we'll take the lowest. My lowest is this first period here, 80 units, $3,200 in costs. What are my highest ones? My highest period of level of activity for labor hours is 120, and the lowest cost and that cost associated with that is 4,500. So I'm going to take my highest overhead cost, subtract out my lowest overhead cost, and then once I do that, I'm going to divide that by the highest level of activity minus the lowest level of activity. Now, and then when we do that, we see that my variable cost or my slope coefficient is $32.50. Remember to do those subtractions on both the numerator and then the denominator before dividing those two numbers. We want to follow the order of operations with that. So the difference between my highest dollar amount of overhead and my lowest dollar amount of overhead divided by the difference between my highest level of activity and the lowest level of activity. And when I do that, my highest level of overhead minus my lowest level of overhead, 4,500 minus 3,200 gives me what? 1,300. Divide that by the difference between 120 and 80, the number of labor hours, which is 40. And when I take my 1,300, divide that by 40, that'll get me 3,250. So now I've determined the slope coefficient or my variable cost. So let's look at step 2. Let's determine the fixed cost by using either the highest or lowest points of activity. So now what I'm going to do is I'm going to take that 3,250. I'm going to take my cost function here, and I'm going to plug that 3,250 back in at either the high point or the low point in order to get my level of fixed cost. I do not want to do any other points other than the high point that we picked out or the low point that we picked out. I don't want to use that 3,250 and substitute it into a different one because that's not going to give me the accurate fixed cost based on those two data points there in our set. So I'm going to plug in my 4,500. I'm going to compute my cost function. I know my total cost, and we're going to pick the high point here. Let's pick the high point where my total overhead costs were 4,500. And my highest level of labor hours is 120. So now I'm going to plug that back in. And I'm going to plug those numbers back in to get my fixed cost. I know my total cost at the highest level was 4,500. So I'm going to plug that there in place of Y. Equals my fixed cost. That's the variable I want to solve for. So equals 4,500 equals fixed cost plus, and now I can plug in my slope coefficient, 3,250, multiply that by the highest level of activity up here associated with the 4,500, and that one was 120. So I want to take my 4,500 equals my fixed cost plus 3,250 times 120. And when I multiply that out and then subtract this amount from both sides, and I've isolated the fixed cost to be $600. So now that I've got that $600 fixed cost, I can now compute my cost function, and I can create that. And my cost function in this case will be Y equals 600 plus 3,250. So I'm estimating some costs, and let's say we're going to estimate costs at 100 units of activity. Well, then I would simply plug in 3,250 times 100. And that would give me what? 3,250 times 100 would give me 3,250 plus 600. And so for if I ran into 100 labor hours, then I would expect my total cost to be around 3,850. Now, again, as we go back to this is a quick way to estimate total cost, but it's not highly accurate. Why? Because that function there is only based on these two data points here. This, the 80 hours and the 120 hours. It's not taking into account the 110 hours and the cost and the overhead cost of 3,900. It's not taking into account the 90 hours of direct labor and the 3,600. So it's only based on these two data points here, the first one and the third one. Why is that a problem? Well, that's a problem because only picking two data points is not going to be representative of the whole thing. So that's why we're going to look at regression analysis. Now, regression analysis is a statistical method or process that's going to estimate the relationship between a dependent variable and one or more independent variables. So we're gonna use a statistical method here. We're gonna run that with you can do that with Excel. You can do it with other statistical software. And this method is better and more preferable than the high-low method. Why? Because it's going to take into account all data points and take all data points in consideration, not just the highest and not just the lowest. So, two types of regressions we can do. We can do simple regression, which is estimating the relationship between dependent variable, which is a total cost, and one independent variable, which is a cost driver. Or we can do multiple regression, because sometimes there are that relationship between total cost and the cost driver. There might be two cost drivers that are driving that total cost. So a multiple regression would be estimating the relationship between the dependent variable, which would be our total cost, and two or more independent variables. Now, we're really not going to get into that. My focus is going to be in this session is just on the concept of regression analysis. And let me go back over here for just a moment before I show you any more information. When we do regression analysis, you're going to see the formula over here in the chart here. And you see the red line here going up. That's my estimated that's my cost function. But the difference is taking all of these data points, not just the highest up here and not just the lowest down there. If it took the lowest here and the lowest and the highest up here, my line would actually look a little bit different, and it would actually be on a little steeper slope. And my slope coefficient would be a little bit higher. So as you can see, this line is running between almost all the data points, and really, except for one, it only crossed one, but it took all the data points into consideration. Another thing, and this is the relationship, this graph is the relationship of machine hours to indirect labor costs. So my cost driver, we're assuming, is my machine hours. That's my independent variable. The more machine hours I have, then my dependent variable is going to be my estimated manufacturing labor costs, my indirect manufacturing labor costs that I'm estimating here. So as I use more machine hours, I expect to have more indirect manufacturing labor costs associated with that. Another thing you will notice is that the cost function is stated just a little bit different when you do it in Excel, but the concept is the same. The only difference is, instead of y equals a plus bx, it has your slope coefficient times x over here first, and then it lists the fixed cost. So in this case, when you're identifying this, what you want to do is see where is that x. That x is going to let you know that the number right in front of it is going to be your slope coefficient. So my slope coefficient is 10.312 plus, and then my fixed costs are 300.98. So in this formula right here, what am I saying? My total costs are going to be $10.31.2 times the number of units I produce, and that will give me my total variable costs, and then my fixed cost of $300.98. Now, just because this is stated a little bit different in the order on the right side of the equation is switched, does not make it any less valid. It just means that the Excel is doing it differently. Excel is putting the variable portion first and then adding to that fixed, whereas in the other one here, let me go back over here. Excel is putting this in front of the BX in front of the A instead of the cost function here, which we see, which we use for the high-low method and for generally stating the cost function. So just because Excel shows it a little bit different, I don't want you to get confused on that. That cost function is the same. It's just two terms are flipped. That's all that it is. So when we're trying to determine which cost driver is best for estimating costs within a cost function, there's going to be 3 criteria we want to meet. The first one is economic plausibility. Does it make sense? Another thing is goodness of fit. When we talk about goodness of fit, we're talking about the tightness, or how tight these data points are in relationship to my cost function, or my line here. The tighter they are, the better that fit. That means that cost function is more, the tighter that is, the greater the likelihood that cost function is accurate, or is highly accurate. It may not be perfectly accurate, but it's pretty close. What if I had data points that were all over the map, and I just, I had some up here, I had some down here, some over here, some over there, some over here, and then I had that line the way it was? Would that make sense? No. I mean, it does. That would not be a very goodness of fit. So the tighter all these data points are, or the closer they are to the line, to my cost function line here, the better the goodness of it. And then there's finally the significance of the independent variable. So when determining the cost driver, it is very important, because management decisions are going to be made on there. As managers, we want to make the right decisions, and having the best and most accurate information is going to be key. So, and this is actually a good way to do that. So now let us take a look at nonlinear cost functions. Now we're talking about, up to now, we've talked about linear cost functions. Let me scroll back here. And we talked about the fact that linear simply means straight. Therefore, the linear cost are those costs that will maintain a straight line, a meaning one straight line. And we talked about total fixed costs will remain constant and unchanged, and variable costs per unit will remain unchanged. So now let's go to nonlinear costs. Nonlinear cost function is a cost function in which the graph of a total cost is not a straight line. That makes sense. Nonlinear, non-straight. Okay, so the graph is not going to be a straight line. So let's take a look at a couple situations here. The first illustration in panel A gives us an illustration where we have the discount, the quantity discounts on direct material. So let's say we're buying this direct materials, and for the first 1,000 units, we're going to pay $25 per unit. If we buy more units above 1,000, then we're only going to pay $15 per unit of direct material. But then let's say a contract says, hey, wow, you guys are buying big, so I'm going to give you a bigger discount. If you buy more than 2,000 units, we're only going to charge you $10 per unit for every unit that you purchase above or more than $2,000. Well, in this case, your slope coefficient is going to be different based on quantity discounts that you might purchase. In fact, a lot of companies will offer their clients, their business customers, quantity discounts. Then we have in the panel B here, in fact, issue panel B and C, step costs, where costs step up as there's more level of activity. So let's take a look at step variable costs. Step variable costs it looks like there's a linear approximation of cost and behavior, but the actual costs are going to be stepping up. What might be causing that? Well, if you think about something, what about if we make something in batches and we have a setup? You've heard of activity-based costing. I'm sure you've talked about it before. You know the term is setup. Setting up, where we set up a machine, create whatever number of units, and that setup will cost, let's say something costs us $100 to set up. So we're changing the machine over, and the cost of changing that machine over from making widget A to widget B is $200. So let's say the cost of setup is $200, and each setup, every time I set up and I'm running whatever number of units within that batch, and then I do another setup to switch over to make widget C or whatever. So an example of a step variable cost function would be setup costs, or maybe even to some degree inspection costs and so forth. So, but setup cost is probably the better one to identify a step variable cost. Now let's look at panel C, step fixed cost function. It has the same thing, but unlike the step variable cost function where the linear approximation looks to be a straight line, we're going to it's an approximation of cost. It looks to be linear, but the actual cost behavior or the actual cost occurrence is in steps. Panel C, where we have step fixed cost, is more of is more clear in the step function, because the hours that we use the furnace to make up to 7,500 hours of furnace time is going to cost us $300. But if we need more hours of furnace time, then we have to, because we have so much demand, then we have to turn on a second furnace, and the cost of heating up that second furnace and keeping it running is going to be another $300. So my total cost between running furnace 1 at $300, furnace 2 costs $300. So my total cost together running 2 furnaces is going to be $600. But what if I have such demand and I have an order for 20,000 units? Will furnace 1 be able to handle that? No, because it can only handle 7,500 hours of furnace time. With 2 of them, I can handle 15,000 hours of furnace time. But if I have an order that's going to demand 20,000 hours of furnace time, we'll not have to turn on a third blast furnace or a third heating furnace. And then that cost, whether I use it or not, is going to be on there, because I got, with furnaces, especially in steel production, you can't just turn those off. They have to go on and stay on. The shutting down process, the turning on process is long, costly, and so it's actually cheaper and actually more efficient just to leave them on. But that's what we want. But so that's an example of, if I have one blast furnace running for steel production, then that blast furnace is going to cost me $300. But if I have demand that one furnace can't handle because I'm stretched to capacity, then I have to turn on a second furnace to pick up the excess excess units that I can't do with my first blast furnace. Then I'm going to use that second one. I'm going to turn it on and leave it on. That's going to cost me another $300. And if I have higher demand, then that is going to be another $300. So now I got 3 furnaces turned on, cost $300 each. So that's $900 total cost. You may say, well, wait, these are linear. Look at these straight lines. Well, when we talk about linear, we're talking about the whole entire line is going to be straight, because while these are linear approximations, but these are in different levels. So we actually have, instead of one linear line going like this, going straight across, or going on a slope, we actually have steps here. So those are examples of some nonlinear cost functions. Another example of a nonlinear cost function would be, or where we have a mixed cost, would be in water usage. If you have to pay for your water and sewage services, you will notice that there are certain charges that you have to pay for every month, and then you're charged additional costs based on how much water you use. So, and then you will have to pay for the water and then pay for water treatment and so forth. So that's where we have an example of mixed costs there. Another mixed cost would be a phone system that we have, but let's say that we have to make a lot of international calls. Our phone company they only give us free calls in the United States. We cannot call Canada. well, without paying extra for it. We cannot call international without paying for it. If we do a lot of international businesses, then we would have an example of a mixed cost, where the cost of the service in and of itself on a monthly basis is the same, but the cost of making international calls to our clients and our supply chain and to others in our supply chain or other parts of our value chain, that would be considered the variable cost of that. So we would have a mixed cost in there. And that's where we can actually use methods like quantitative, like a regression analysis and high-low method to get a better sense of what my total phone costs are going to be throughout any given period. So that is our session on cost behavior. Thank you for being with me, and I look forward to seeing you again.